So thank you, Stephen, for inviting me. And I know that it's a probability seminar, and I'm not giving a talk on probability. So take it in the spirit of trick or treat, and hopefully, it will be a treat and not a trick. Okay, so I'm going to talk about submodular function minimization. So I'm going to explain what that problem is and why it's important. And in particular, I'm going to look at parallel algorithms for them. But the whole talk is sort of quote unquote bad news. I'm going to show that some things that we would hope to do is not possible. It's a lower bound talk, but and the main takeaway maybe, if you have not seen what submodular functions are, maybe those things and maybe the construction that we come up. Okay, so let's begin by good. So submodular functions. So these are set functions. So there's a universe which I'm going to finite universe which will have capital N elements. So the capital N will be always used to denote the size of this universe. And a set function assigns a value to every subset of the universe. And then we're going to assume that this, for most of the talk, that the range is just integers. Okay. So what makes a set function submodular is this decreasing marginal utility property, which says the following. So you take a set S and take a superset T of it, and take an element I, which is not in T and therefore not in S, and you look at the increase in the function value when I add I to each of these sets. So this partial I f of S is basically saying how much the function value increases when I add I to S, and similarly this delta I f of S T would be how much the function value increases when I add I to T, and it must be that the increase is more for the subset than the superset. So if you think of f of S as the happiness you get if S is the sort of set of items given to an agent, then delta I f of S is the marginal utility of this item that you don't have, given that you already have S. And this says that if you have more, then your marginal utility is diminished. So that's the connection with economics. Now, I would make a remark here that this increase could be negative. It's not necessarily an increase. So in particular, these marginals could be negative. And for the problem that we're going to look at, it will be negative. And the example I like to give here sometimes is, imagine that, this is the happiness that you obtain when eating mangoes. So the 8th mango might give you a negative happiness rather than a positive happiness after you have eaten 7, depending on the person. So that's a definition of a submodular function. And just to give an example, imagine the universe is the set of possible points in a room where you can put sensors. And if you put a sensor at a certain location, this green oval is showing which of the areas are covered by the sensor. And given a subset of locations, f of A, you can think of the value as the total area covered in the union of these ovals, the area covered by the sensors. So I claim that such a coverage function is a submodular function. Just to see this, imagine you have sensors open at locations 1, 2, 3, and you decide to open at a location J. Then this red zone is the marginal utility of, or marginal increase of this function value when you add J to this set 1, 2, 3. And if you added J to 1, 2, a subset, you'll be covering a bigger, the green zone contains the red zone, and therefore the marginal utility of the subset is bigger. So this is a proof by picture that this coverage function is a submodular function. Now, as stated, this function is monotone. The more sensors you open, the larger area you cover. But you can imagine a function which is the area covered minus the cost of opening the sensors, and that could be a non-monotone submodular function. Okay, so maybe I should have said it before the beginning of the talk, but if you have any question at any time, please just unmute yourself and ask them. Okay, don't feel shy about it at all. Okay, so that's an example of a submodular function. But submodular functions arise, in many places. So in particular, cut functions in graphs. So if you look at the number of edges that you need to delete to that cross a subset, is a submodular function when the subset is the set of all possible subsets of vertex set. And in their generalizations in directed graphs and hypergraphs, these are very well-known submodular functions. in an information theory domain, if I have a bunch of random variables and I look at the Shannon entropy of any subset of them, so they're not necessarily independent, then that Shannon entropy is a submodular function of the subset of the random variables that you pick. And maybe another example from a different domain, if you have a positive definite matrix, a square matrix, and I take, if you take a subset of rows and a similar subset of columns, and you look at the determinant of this A as a submatrix, take the log of that, that is known to be a submodular function. So submodular functions keep up in many, many places. And so if you've never seen them before, maybe that's maybe the biggest takeaway from this talk.
A question?
Yes.
Some of these examples don't seem to have integer values.
Yes.
Integer values important or?
No, so integer values is not important. They can be real valued. And it's just that the submodular function that we will be talking about in the talk will be all integer values, but they could be real values.
Okay, thank you.
Thank you. Good. And so they arise in various applications. But the other reason submodular functions are super important is that they make certain optimization problems tractable. So in particular, this is the problem we'll be looking at. So the problem is SFM, submodular function minimization, which just asks what the name suggests. It's a function defined on all subsets of the of this universe. Find the subset where it takes the minimum value. So note that if the function was monotone, if the marginals were always increasing, then the answer is the empty set. But the function can go up and down, and so this problem is a non-trivial problem. How is the function given to us? So the only thing we'll assume about the function is this evaluation oracle axis. There's a black box. You ping for a set S, out comes f of s. That's the only access to the function. Nothing else other than submodularity will be assumed. And even then, so there are 2 to the n possible subsets. You have to find the minimum. So before I go on and say what is known about this problem, let me make a few assumptions, not assumptions, but sort of baseline comments. We'll assume that the empty set evaluates to 0. This is without loss of generality, because if I can, I can scale the additively every value by any constant, and the function remains submodular. So I can always scale it. If the empty set is not 0, I'll scale it by that negative of that. And therefore, the minimum value of this function will be a non-positive number. So in particular, if it is not the empty set, it would be a negative number. That's the thing we want to find. And I'm going to use M, although we'll really not use it for the most of the talk, but capital M is often used to define, denote the maximum absolute value of this function when the range is integral. And I say when the range is integral because I can multiply the function by any value and it still remains submodular. So M is only well defined if I sort of have a granularity. So if the range is integral, capital M will be used only when the range is integral. But if the range is not integral, one can also talk of additive approximation. So you can scale the function so that the function is within -1 and 1. And an epsilon approximate minimizer is a set whose value is maybe bigger than f star, but not by more than epsilon. So that's just notation, and which I might come to approximation at the very end of the talk. Okay, submodular function minimization is this is the problem. What's known? So it's a remarkable thing that although the function there are 2 to the n set, it's defined on 2 to the n values points. The minimum thing can be found using only polynomial many queries. So polynomial in capital N. And this is a deep result. It was first established via this work of Groche-Lowa Schreiber in the setting of a bigger thing of ellipsoid algorithms for convex minimization. And in particular, the reason why this is tractable is that you can cast submodular function minimization, which is a discrete optimization question, or to find something over this 2 to the n possible subsets, as actually a convex optimization question in a continuous setting. And I'm not going to talk about that, but that's the real connection. That this problem is tractable because of this connections to convex optimization. And that's what, and once you have this fact that you can do it in polynomially many queries, after that, there are like hosts of algorithms which actually get there, okay? And this slide, you don't have to read this. The thing that maybe one should take away is this point here. And hopefully you can see my cursor. Now, the current best, which is from this year, a work of Haotian Jiang, says that this polynomial is actually n square, roughly. Okay, So it's n square log n. So you can make, there's an algorithm which makes n square log n queries to the submodular function and will return the optimum. There's a slight catch here that the algorithm's running time itself after making the queries might be exponential. But if you want really polynomial time algorithms, then this is the answer. So basically n square log n and maybe capital N. We are not going to really bother about running times here. So if you just want to think about how many accesses, how much access do you need to the submodular function, answer is quadratic. And I think this is remarkable, right? As in, there are 2 to the n possible things, and the only property of submodularity is used to find the minimizer in only quadratically many things. And in fact, we don't know what is the right answer here. So we cannot rule out, for example, an algorithm which makes only 10 times n queries. So that's not ruled out, and yet the best is quadratic. So there is a slight gap here, and it's a titillating question to figure out what the right answer is. That's not going to be the topic of this talk, but it's a question that really interests me. Okay, so the takeaway is that this problem is tractable, which is, and I'm not, unfortunately, not going to tell you how it is done in this talk, but the answer is like n squared. So what is this talk going to be about? It's going to be about slightly different thing. It's going to be looking at parallel version of this question. So what does parallel version mean? So this problem, submodular function minimization, falls under this, in a sort of query access model. There is an object which you're querying, then you're running some algorithms, and then you maybe query again, and then you run some algorithms. So in any such query access algorithm model, there's a notion of adaptivity. So in particular, the simplest, the non-adaptive algorithm would be as follows. You make all the questions, you ask, you have a fixed set of questions, you have a fixed set of subsets which you're going to query. And depending on the answers, you'll look at the answers and you'll do some work, and then you'll figure out what you want. So in particular, for submodular function minimization, you'll figure out the minimizer. So that would be a non-adaptive algorithm. More generally, an R-round adaptive algorithm, an algorithm with R rounds of adaptivity, asks questions, but the ith rounds questions only depends on the answers that have seen for the first I minus 1 rounds. And so it runs for R rounds. So maybe if R is equal to 3, it runs for, it asks questions, gets answers, then looks at the answer, asks a different set of questions, looks at answers, and there's a third round of questioning, answers come, and then it figures out the minimum. Okay. So what we're interested in is not just the query complexity of submodular function minimization, how many queries do you need, but how few rounds can you make these queries in. Okay, so there's a notion of, this is related to the notion of depth in parallel computation. So if you think of processors which can give you answers to the submodular function queries, and every round you can parallelize the queries across the processors, and then there is a communication where they all give the answers, and then you figure out something, and then you do another round. So there's a notion of depth in this parallel computation, and the question we're interested in is, are there low depth algorithms for SFM? So note that there is a non-adaptive algorithm which asks the function value in all the 2 to the n points. And of course, the interesting question is, in how few rounds can you actually minimize the submodular function, with the caveat that the number of queries is not like stupidly high. It's at most a polynomial. Maybe not n square. I'm allowing you n to the 100. Can you do it in maybe 2 rounds or 5 rounds or something? So that's the question that we will be focusing on. So any questions about the question? Good. And now all existing algorithms, the whole list of algorithms that I had shown a few slides back, all of them run in they take at least capital N rounds. In fact, at least n log n rounds. Okay. And so we would like to have something better. And that's the question that we answer in some sense. Now, it's not too difficult to show that if you look at only non-adaptive algorithms whose questions are fixed upfront, you need to really ask almost all the sets. Okay, so and the reason is, if you have missed out a bunch of sets, then I can design a submodular function which sort of minimizes in a set that you've not asked, etc., etc. So it's not too hard. It's not trivial, but not too hard to prove that non-adaptive algorithms must make exponentially many queries. But even showing that a 2-round algorithm does not exist, which makes like polynomially many queries in each round, is not trivial. And it's not just in the submodular function minimization setting. In general query access setting, saying that non-adaptive algorithms cannot exist is often much easier than showing that 2-round algorithms don't exist. Now, of course, that is true, but there's a qualitative difference between these two things. And sort of maybe you can already feel that once you understand it, because the second round questions can depend on the answers to the first round. So this is a non-trivial question. And so it was only last year that in an influential paper, it's a great paper by Eric Balkanski and Singer, who showed that the submodular function minimization cannot be done in constantly many rounds. In particular, if you want the number of queries to be a polynomial, any polynomial, then the number of rounds must be at least roughly log n. So this rules out constant, depth submodular function minimization algorithms. However, it does not rule out the depth of something like log n or log square n. And there is if you think about, if you know a little bit about the connections to say circuit complexity, this depth, if you can achieve something in depth which is like polylogarithmic, a polynomial of log n, like log square n or log cube n, that's actually pretty good. It's related to the circuit class NC. And so if you could do efficient submodular function minimization, efficient here meaning polynomially many queries, in something like log square and rounds, that would be pretty good in a certain, it will be pretty surprising. Unfortunately, as I sort of alluded to, and it's alluded to in our talk's title, the answer is worse. So the result that I'm going to talk about today is that submodular function minimization is tractable, it's efficient, but it has to proceed in many rounds of questioning. So how many? It's not quite omega n. We can prove that you need at least roughly cube root n rounds. And there is still a gap between cube root and an n. And I don't know which, that's actually one of the questions that I'll sort of leave as an open question. I don't know where the answer is. I don't even know what's the right guess, but I would be surprised if this is the right answer. Okay, so this is the main result. So that submodular function minimization is tractable, but not super parallelized. Okay, so my goal for the STOC is sort of describe the kind of submodular functions here. So I'm going to take my time and describe them. I'm not going to go into the full proofs, but I would like to give you an idea of how these submodular functions look like, this difficult submodular functions. But before I jump into that, let me at least have a slide on where this result lies in the bigger scheme of things. So I already mentioned that submodular function minimization is tractable because it has connections to convex optimization. So one could ask, what is known about convex optimization per se? Like, so that again, and for general convex functions, you often have this. You have this epsilon here, which you want to be epsilon close to the optimum value, and not solve it exactly. Is there a depth versus query trade-off here? So this question was already asked in the 90s by Nemirovsky, and his result roughly shows that if your algorithm is making polynomially many queries, so n is here the dimension of the space in which I'm doing convex optimization. If I'm making polynomially many queries, then I do need to make so convex optimization is not parallelizable, highly parallelizable. It will require again cube root n log 1 over epsilon rounds. And now, if you see this cube root n, and there was a cube root n in the previous slide in our result, and I think the reason for the cube root n is sort of same from a mathematical standpoint, like why it comes to cube root n. And so we'll get to this cube root n hopefully by the end of this lecture. And the reason why this cube root n is shared in both these results is the same, but the functions are very different. So Nemirovsky's function is not anywhere close to a submodular function. The sort of the rationale, connections with standard deviation, etc., and we'll come to that, is why this cube root n comes up. It's conjecture. I think he conjectures that this answer should be m, but I don't know if I will give this conjecture for SFM as of yet. This was a paper ahead of its times. There have been improvements, and I will not belabor them. But basically, if you think about the dependence on epsilon not to be log, epsilon is a closeness to the approximation, but something polynomial, then the answer changes a bit. And so this is, I'm just mentioning this, but if you want to sort of apply to submodular function minimization, this sort of does not give anything, because I really want to get exactly close. Epsilon becomes something like 1 by capital N. So that's one set of results, and there are other papers which I've not mentioned here, which look at sort of the parallel version of convex minimization. There is a second collection of results on submodular function maximization. So submodular function is tractable in the minimization world. In the maximization world, the submodular functions come where there are greedy algorithms which actually get them. In fact, there are people in the audience who have worked on these things. And there are also people, then again, Balkanski-Singer in a different paper asked, what is the trade-off between queries and the number of and the depth of the algorithm? And there the answer is sort of log n is the quote unquote correct answer. So they prove that any function, any algorithm which makes, okay, so these problems are NP hard, so you want approximation algorithms. So any approximation algorithms must make log n rounds, log n by log n, and roughly you can get similar approximation factors in that many rounds. So it sort of matches. And this is in the case of constraint maximization, and then people looked at unconstrained maximization, where the answer is actually very interesting, that you can get an algorithm which gets close to the best non-parallel algorithm, but making only like 1 by epsilon rounds of complexity, and the approximation factor gets hit by an epsilon. So this is just to give, if people are familiar where this result lies. So I'm going to sort of dive into the ideas of the construction. Again, maybe if you have a question, maybe it's a great time to ask. I'll take a sip of water. Okay, so I'm going to try and describe how do you prove a result which says that any submodular function minimization must proceed in many rounds. And the idea in the class of submodular functions, and maybe this is also a takeaway from this talk, is this particular way of looking at submodular functions. So this class is called partition submodular functions, and it was introduced in this paper by Balkanski and Singer. So my universe is N, and imagine P1 to PR is some fixed partition of this universe. Okay? And this partition I'll change, but for now it's fixed. So a submodular function is called partition submodular if it looks the following way. You take any subset S, the function value of S is actually a function, a different function H, of the various amount of stuff you get from each part. So I look at how many elements of P1 does S contain, how many elements of P2 does S contain, how many elements of PR does S contain. So I'm looking at these cardinalities. So these are integers. And there is a function H which connects all these integers. So if my submodular function looks like this, then we call it partition submodular. Okay. And if I fix this partition, then every set S has a signature X, where Xi is counting how many elements of Pi this has. Okay. And the function value f of S is nothing but a different function H evaluated in X, where X is some r-dimensional integer vector. So is this clear? So maybe a few examples. So one simple example is the function value of S is just some concave function of the cardinality. So I've just put square root here. So here, the partition is the trivial partition. There's just one part in it. So the number of parts of small r is 1. And the function H is just the square root function. So it takes the square root of the cardinality. A slightly more nuanced is thing which, it has two parts. The partition has two parts, and I take the sum of the square root. So h function is square root of x1 plus square root of x2, and f of s is defined like this. So this is a separable. So this h is a separable concave function. It takes some function on the first coordinate plus some function on the second coordinate, and a slightly more, things which is that it need not be separable is where I take the product of these. Okay, so but there could be many such other examples. So again, so there is a partition, and the number of parts is r, and the function value on a set is just it just looks at how many things from each part it is taking, and it's a function of that. So if r, the number of parts, is 1, then it's just a function of the cardinality. Otherwise, it's just a function of how these sets fall in different ways. So in some sense, this r, this number of parts of a partition function, is a measure of the simplicity of the function. At the extreme, where the partition is a trivial partition of singletons, then any submodular function is a partition submodular function. But as the number of parts becomes smaller and smaller, the submodular functions in some sense become simpler and simpler. Okay, so so this is the definition of a submodular partition submodular function. So this is the definition again. So it looks at this. It's a function of the various cardinalities. And what do I need about this function h? So this h is a function now defined over in some sense the hypergrid, right? It's the integer grid it's defined on, and I have the same. So f is submodular if and only if h is also submodular, which basically says that the discrete derivative of a point, so the delta I h of x, which is nothing but I increase x by the ith coordinate of x by 1 and look at how much the function increases by. This should be only bigger than delta h of y whenever y is bigger than x. So y is just x plus some other coordinate. I should have this marginal should only go down when I go from x to y. A pictorial way of thinking about this. So I'm going to now show a picture for r is equal to 2, because that's the two-dimensional things are easier to draw. So r is equal to 2, and each of these, so it's a very simple function. So each of these parts has maybe 4. So P1 is size 4, P2 is size 4. And I'm looking at the function value. So this picture is indicating what the h thing is. So in particular, a point here, which is 3, 0, says I take 3 elements from this part, maybe it's P1, and then 0 elements from this part. What are the numbers on these edges? So the numbers on these edges are these delta I h of x, right? So I'm writing 1 here means that when I go from this point to this point, the function value increases by 1. When I go from this point to this point, the function value does not increase. When I go from this point to this point, the function value goes down by -1. So this is a different way of representing this function h just by the marginals. What does submodularity tell? Submodularity says that if you go from left to right, so you go from on this edge and you look at the edges that you encounter, those numbers can only decrease. This is what this point says, the 2, 2, 1, 1, 1, 0, 0, -1. Similarly, if you go up anywhere, the function values can only decrease. So 2, 1, -1, 2, 0, -1, 1, 1, 0, 0. And this is just in 2D, but in arbitrary dimensions, that's what submodularity is saying. So you have these, so decreasing marginal utilities mean in a picture like this, where I'm describing the function by the marginals, I have diminishing things in every way I go in the positive order. The other thing one needs to be careful about is that when I want to describe a function by its marginals, is that there is consistency. So if I go from this point to this point like this, and I go from this point to this point like that, from top and left, right, and then or right and top, I must have the same values. So some of the values must be the same. So 0 plus 0 should be equal to 0 plus 0. Similarly, 0 plus -1 should be equal to 0 plus -1. So this is a way of describing this function h. And once you have this, you can see the function value at this point is, so I start at 0, then I go up 1, 1, 0. So the function value here is 3, then it goes to 2, then it goes to 1. So that's the function value here. And so this is a different way of representing every function value. Okay. So I'm belaboring this point because this picture will come up again to give an intuition of the construction. Okay, good. So now I can describe the framework where these difficult functions lie. And this framework was already there in the previous paper. So the idea is to construct this partition function H, this sort of quote unquote nasty partition function H. So once you tell me H, once you tell me the partition, a submodular function is defined. So there are some properties that are needed in H. One is that it has to be submodular. So when I go from left to right, the function value should decrease, or I go from top to bottom, the function marginal should decrease. The H will be so defined such that the minimizer of this submodular function, when a partition is fixed, there will be only one minimizer. It will be quote unquote the last part. So there's only one minimizer PR, which any algorithm needs to figure out. Okay, so any algorithm which is saying that I can find the minimizer must find the last part. So this partition is not known to the algorithm upfront, and yet it has to find this quote unquote last part of the partition. And the main kicker, which leads to this lower bound, is the following: this H has to be defined, has to be designed in such a way that if you make only a few rounds, so any I round algorithm, well, when you make queries, so imagine this P is hidden by some adversary. When you make queries, you get to learn something about the function, and therefore you get to learn something about this partition. But any I round algorithm does not learn anything about the parts I plus 1 to R. So in particular, if you look at a one round algorithm, a non-adaptive algorithm, it might learn which part is P1. It might learn the first part of this partition, but it is completely confused between the parts 2 to R. Let me belabor this a bit. So the way to think about this whole lower bounding procedure is we're going to construct this H in a way, and that the sort of the last third of this talk will be based on how to figure out this H. But think of P as a random partition, random equipartition, if you want. When you fix H and you fix P, you get a fixed function. But otherwise, since P is a random partition, you get a distribution on submodular functions. Now, suppose you make a query at set S. Suppose you are in the round 1 and you make a fixed query at set S. Then, if P is random, right? So P is random. The signature of S with respect to P. What is the signature? X1 is counting how many elements from P1 does S have. X2 is counting how many elements from P2 does S have, and so on and so forth. So if P is a random equipartition, then I claim with high probability the signature will be looking very similar to each other. So the number of elements from P1, number of elements from P2, number of elements from PR will be roughly the same up to standard deviation. And what this indistinguishability says is this crux of this constructing this H is based on the following. For any such quote unquote balanced X, where the Xi's are roughly the same, so for example, in the first round, this for balanced X, the marginal of this function H that you want to construct on X, the ith marginal, is the same for all I bigger than 1. So it might be, so the I equal to 1 might have a certain marginal, but every other I has the same marginal, which means that after making this query, the algorithm is confused between the partition P1 to PR and P1 to P1 and Q2 to QR, where Q2 to QR is a random repartitioning of this last R minus 1 parts. Again, why? Because for both of these, you get the same signature. And if you have the same marginals here, you don't know which so if delta 2 h of x and delta 3 of h of x are the same, you really don't know which marginal is, which coordinate is in part 2 and which coordinate is in part 3. So this is the meaning of what learns nothing is. So the construction of H, and this is where the hardness is, that it somehow has to look same on signatures which are sort of balanced, and yet it has to be submodular, and yet the function has to be minimizing at the last part. So there is a tension among these properties, and I want to sort of get this tension across to sort of appreciate the construction. So for understanding the tension, let me assume that there are three parts. P3 is the minimizer, and I'm currently looking at the slice. So the hypergrid is actually a cube now, right? It's a three-dimensional cube, and for simplicity, I'm looking at the slice where the first coordinate is 0, and I'm drawing what H looks like in this P2 P3 plane. And again, for simplicity, let's assume that all the marginals are either -1 or 1. Okay? It need not be like that, but suppose they are. So what does it mean that F, so P3 is the unique minimizer. So P3 is sitting here, and the value of the function here must be strictly negative, because otherwise the empty set is also evaluating to 0. So which means when I start at the empty set and I go here to I take everything of P3, I ultimately get a negative number. So the sum of these marginals on this line must evaluate to a negative number. And by submodularity, I must have some pluses, +1s, and then -1s. And the number of -1s, so the length of this -1 should be more than the length of this +1. So that's what one of the necessary conditions here. Okay, so this is from the fact that P3 was a unique minimizer. Now, the fact that P2 and P3 cannot be distinguished means that if I pick a point which has roughly the same amount of things as P2 and some same amount of things as P3, in particular, any point on this diagonal, the marginal with respect to P2 and the marginal with respect to P3 must be the same. So these values here, the marginal of H with respect to P2 and these values here with respect to P3 must be the same. This is the fact that if I cannot distinguish between P2 and P3, this must be happening. But I do know what the value here is. If the value here is -1, submodularity tells me that this has to be -1, because I only decrease when I go up. And if this is indistinguishable, this becomes -1. And if this becomes -1, by submodularity again, the marginal here becomes -1. And in particular, the whole line here becomes -1. So if there were 3 +1s here and 5 -1s here, I also get 5 -1s here. So the marginals of the function, when I'm traveling from this point to say this point, well, it increases for 3 times, then it decreases 5 steps, so I get -2. But now maybe I increase here. I might be decreasing, but the worst case I'll increase here. But then again I decrease here, which means that the function value here is actually going to be smaller than the function value here, which is contradicting the fact that P3 was the unique minimizer. So hopefully this sort of gives an idea of the tension. If I assume that the marginals are only +1, -1, and I have sort of these three properties, they sort of, it's hard to orchestrate them together. So maybe that if that has gone across, then I sort of been successful here. So what do Balkanski-Singer do to get rid of it? So they have this idea, what they call masking. So in this slice, we had assumed that x1 was 0. So the set S does not pick anything from P1. But in that case, x2 and x3 also should be 0. So this picture was in some sense cheating a bit. So what Balkanski-Singer's idea, and this is an extremely, extremely high level idea. They need to do a lot more work. But they basically said in round 1, the set P1 acts as a mask. Okay, what does a mask mean? It means that if you pick a set S as a query, and so x1 is the amount of stuff it gets from P1. If that number is small, if that number is smaller than P1 by 2, then all the marginals for 2 to R is +1. And if it is bigger than 2, then they're all -1. So it's sort of the marginals for, say, coordinates 2 to R for at a given point X only depends on really how much stuff you get from P1. And this is what is indistinguishability, right? Because all the marginals for the coordinates 2 to R are the same, and therefore you cannot distinguish between P2 to PR. Okay. Now this is this is again an extremely high level idea, and they need to do a lot more work to, orchestrate this. But this shows that there is the bottleneck of log n comes from here, because now note that if this is the picture, now look at what the value of the whole set is. Suppose I take all the elements from P1, and after that I take the elements from P2, then P3, then P4, and then all the PR. Well, if I take all the elements from P1, everything gives me a -1. So the function value at this will give me minus P1, minus P2, minus P3 up to minus PR. And maybe the first P1 elements give me +1 all the time. So I get plus P1 for that. So if this whole set is not supposed to be the negative, it's because the minimizer is PR and not the whole set, I must have P1 to be much, much larger than the sum of the remaining parts. And inductively, P2 must be much larger than the sum of the remaining parts, and so on. And this sort of puts a bottleneck of log n on the number of rounds that is at all possible. So their log n by log n comes, they can get it, but their technique is sort of, it has a bottleneck of log n. So this sort of gave us hope that maybe we can get a log n depth algorithm. But unfortunately, that is not the case. So the way out of it, and this is maybe what I will try to impress, that what we really need is that if a vector is balanced, then the marginals should be the same for every j which is bigger than I. Instead of having a mask, strong mask, we actually design an H where this quantity only depends on the norm of X. Okay. In particular, for the case of Balkanski-Singer, if you look at the point which has everything of P1 and nothing from 0, Balkanski-Singer will say, oh, I'll have marginals -1 for all 2 to R, but our function will actually give +1, and therefore it sort of breaches this bottleneck of log n. So let me give you some ideas of our construction. Again, this is a lower bound construction, so at some level this is just one fixed function. So I want to describe this construction, this H function, because once I tell you H, the submodular function is given by the random partition. So I want to describe this function, and maybe then I'll adjourn. I want to describe this function H. This is an R-dimensional function via its marginals. Okay. So the partition is going to be, equipartition. So every part P1 to PR will have small n elements, and the size of the universe is n times R. All the marginals will not be, it will not be -1 +1, but I'll also have zeros. And they will look in the following way. So given any X, so X is a R-dimensional vector, integer vector, the marginals at X for H will look like this. So here are the coordinates 1 to R. Given X, I'll figure out two locations, A, X, and BX, or just A and B. And these delta i's will be +1 till A, 0 from A to B, and then after that -1. Okay, so this is how the marginals will look like. So to complete the description, I actually need to figure out what A and B is. And A and B's will depend on suffix functions. Okay, so I'm going to look at, given X, I'm going to look, so LTX is basically saying, so X is a vector. LTX says how much mass does X have from the coordinate T up to N. And I'm going to tell what the function exactly is, and then I'm going to run an example. But A and B are going to be the indices where LT is maximized. And after that, once I fix A and B, the marginals are fixed. So let me just dive right into what the suffix function is. It's basically the suffix, so summation xi, LT is summation xi, I bigger than T, except I count the contribution, so it's a negative contribution till it reaches some threshold tau. And there is one extra thing, I subtract gamma from the end because of technical reasons. Okay, so what are these parameters? So the threshold tau is roughly half the size of every part. So till I get to the half, I don't really contribute. I contribute negative to LTX, but I shade it by one standard deviation. Okay, and this standard deviation is basically in the twiddly xi is twiddly xi plus 1. That's where I need to shade this a bit. And gamma is roughly the standard deviation times r. So just to run an example, imagine r is equal to 5 and n is equal to 10. So each part has numbers. So each x is every coordinate takes a number between 0 and 10. And I have a point like x, and I want to figure out what the marginals are. So let's suppose these are the functions, and tau I just chosen to be 4 and gamma equal to 4. So I'll not do the calculations, but if you sit and do it, you will see that the LTXs look like this. Okay. So the qualitatively, what I want you to take away is when x, so n is 10, and these numbers are basically saying I'm aggressively picking stuff from all the parts. So it's like I'm sampling a set very aggressively. And then the LTXs are decreasing non-negative numbers, as is expected, because all of these will become positive. So the largest LT will be here. And so the largest AX is 19, so the coordinate 1. The second largest is coordinate 2. And therefore, the marginals for at this X is given like this, which means that the first part, if you add something, the function value does not increase. But if you add something in any part other than the first part, the function value is going to go by -1. The key thing is that these are all the same. Okay, so you cannot distinguish at this x, you cannot distinguish between 2, 3, 4, 5, but one will be distinguished. The other extreme is when I pick an x where I hardly pick anything from any part. So all the numbers are small. And again, if you do the math, you will get that the numbers are now negative, because, and this is negative because tau is roughly half the size of 9. So if you all the contribution here is negative. And then AX and BX don't exist, because AX and BX are the largest indices which are positive, and therefore all the marginals are +1, which is saying that if you pick X which is very small, every coordinate is going to give you +1, and again you cannot distinguish between any of the coordinates. So let me skip this one and show an example of the following form. Now suppose my algorithm does learn something about the first part. Maybe it has learned, it's running its second round, and it says it realizes that the first part is bogus, so it does not sample anything from the first part. But among the parts 2 to 5, it's completely confused, and it picks almost an equal number from each. Then again, if you do the math, what you will see is that the first part will give you +1 because you didn't pick anything from it. The second part will reveal itself, but 3, 4, 5 is still indistinguishable. And in particular, the only kind of vectors which reveal a lot of information are of the following form, where you pick something and then you pick nothing from a part, pick something from a second part, and then you pick nothing from the third part, and you pick something from the fourth part, and so on. Such vectors will have marginals which sort of will give you information about different parts. But the point is, if you don't know anything about, so you're at this point where you're very confused about how the partition is between the parts 2 to 3, 4, 5, a query made almost surely will never look like this, where it picks a lot of items from the second part, picks a lot of items from the fourth part, but completely misses the third part. That's a very improbable thing to happen. And rather, the probable things to happen are of the following, where everything is sort of equally balanced. And when things are equally balanced, because of the way the suffix functions are designed, A's and B's are going to be adjacent to each other. And therefore, you will maybe discover one thing, one part that will reveal itself, but you'll be completely confused among the remaining parts. Okay, so that's what I really wanted to say. And maybe this is the description of the hard function. It's actually I've described via the marginals, but actually the function is just the L1 norm minus 2 sup of linear functions. So I look at all these suffix functions, which are just linear functions. I pick the ones that are the largest and the second largest, and then I cap it off at 0. So this is it has a very concrete, simple definition. But the way we came up with this was via this margin. So I'm going to skip the sort of the description of why they are submodular and why they're indistinguishable. In this, hopefully the examples show that when things are balanced, the A's and B's are actually next to each other and don't discover anything. I want to sort of, the last technical thing I want to sort of end with is why this cube root n. So this is the function value. And what we really want is the minimizer is, the unique minimizer, the last part. And the tension is, of course, that things are giving negative marginals. The set that one is most worried it is the all one set where I've picked everything. So if you plug in this function, the all n vector, so you take everything from every set and you evaluate this h at the all n vector. So I'm taking basically the whole set. Then if you evaluate this for these values of tau and gamma, you see that the answer is small n by 2, which is the size of the part, minus r root n. This root n is because of the standard deviation, which I need to give because if you pick a random thing, you can be off by 1 or 2 standard deviations. So you need to give some padding of root n. And you get that the function value at the all n's vector is something like this. And you want this to be positive, because if this is negative, then the all n's vector is the minimizer and there is nothing to hide. And so if you do the math here, you'll see that the number of parts is roughly square root n, where n is the size of each part, and which means that when you look at the size with respect to the whole universe, it's cube root of the universe. And this sort of syntactic thing is also happening in the Nemirovsky function. So the cube root n is coming for the same sort of reasoning, one square root n because of the standard deviation, and one number of parts times the n is the whole universe. So that's sort of the thing I wanted to talk about technically. So let me sort of conclude now. So if you have not heard of submodular functions before, maybe that's the most important take-home point. They're amazing objects and you can minimize them. So minimizing them is tractable, but the takeaway from our work is that it's not quite highly parallelizable. In fact, maybe it will be very interesting to have an algorithm which makes number of whose depth is actually smaller than capital N, like small o of capital N. And maybe this partition submodular functions which arose because of the study of this lower bounding question. But I feel that they are also a nice way of capturing the simplicity or difficulty of complexity of submodular functions. And they're worthy of more research, I believe, this partition submodular functions. And so a few questions I'll end with is one question I already asked: can you do it in sublinear number of rounds? I have not. We have been looking at exact algorithms, but we can ask about, suppose I want to do epsilon additive. Can you do that in much fewer rounds? And that answer might be yes. And then if I look at partition submodular functions in that special case, what can you tell anything about minimizing such functions? So the lower bounds that we got, we don't have matching upper bounds. But finally, the big, titillating question is just submodular function minimization without any parallel or anything. Is n square the right answer, or can you actually get better than that? So with that, I will end this talk and thank you for your attention, and I'll be more than happy to get questions.